Congruence is a very important property which also has applications. For example, in RSA crypto system, we need congruence. We use basically congruence. Okay, and even in group theory that we are going to discuss later, or ring theory, is congruence will actually give us lots and lots of examples. Okay, so it has both theoretical and practical applications. And what is a congruence? Let's start with a fixed positive integer n. Okay, we say that two integers a and b are congruent modulo n, which we write as a equivalent to b mod n. That's, or you say a congruent to b mod n, if n divides the difference, n divides a minus b. Okay, so a minus b is a multiple of n. So a minus b is a multiple of n, that is same as n divides a minus b. And of course, you can see that if I take n to be 1, it is not so interesting because 1 divides any integer. So if we take this integer to be 1, then it will not give us anything special. It will cover all, the equivalence class. It's too far ahead, but yeah. So, n equal to 1 gives a trivial definition, but otherwise, and of course, we are saying positive because we cannot divide by 0. So, but any other positive integer will do. For example, let's say 23 is congruent to 5 modulo 18, because if I subtract, I get in fact 18 itself. Or 31 and minus 5, because if I subtract, I'll get 31 minus 5, it is 36, which is divisible by 12. Okay, so we are saying that in short, 31 is congruent to minus 5 mod 12. Okay, that is the relation. And of course, when n does not divide, we say that a is incongruent to b modulo n. Okay, and we write like this: a is not congruent to b mod n. For example, 17 minus 3 is not divisible by 5. Okay, so we say that 17 is not congruent to 3 mod 5. Okay, that is the definition. Two integers a and b are congruent if their difference is divisible by n and some fixed positive integer. Okay, so let's see what it gives. So we can view this congruence modulo n as a relation on the set of integers. Remember or recall what is a relation. Relation on a set, basically you can view it as pairs a and b. We say that a is related to b if that pair is there. So in other words, it's like a subset of z cross z. A relation on the set z is a subset of the Cartesian product z cross z. What is a Cartesian product? Like pairs a comma b, where a and b both belong to z. Okay, and we can also say that it's a is related to b under that Cartesian product of the subset of the Cartesian product. Okay, so anyway, so that's a relation. So what is what are the properties of this relation? First of all, it is reflexive. What does it mean? That means every integer is related to itself, or every element is congruent to itself. Every integer is congruent to itself, whatever n I take, because their difference will be 0, and 0 is divisible by any integer. Okay, this type of relation which satisfies this property is known as reflexive relation. Okay, reflexive. Every element of the set is related to itself. Okay, that makes it a reflexive relation. A relation on a set S is reflexive if every element is related to itself. Here our set is Z, set of integers. Okay, so we say that any two integers are congruent modulo any, and whatever n we are taking, although this is a fixed n for us, so this is reflexive. And this property is known as symmetric. What is symmetric? That if A is related to B, then B is related to A. So if A is congruent to B mod n, clearly B is congruent to A mod n. Okay, that makes it reflexive. Clearly, because if n divides A minus B, certainly n also divides B minus A. So it's clear that this property is satisfied, and this property is known as symmetric property. Okay, it is the symmetric property of a relation. And the relation here is congruence modulo n. Okay, and it is transitive, meaning if A is related to B and B is related to C, then A is related to C. That's what transitivity implies. But in this case, it is clear. For congruent, if the relation is congruence modulo n on the set of integers, then if A is related to B, that means n divides A minus B. And if B is congruent to C mod n, that means n divides B minus C. So n divides A minus B and n divides B minus C. So you add them, A minus B plus B minus C. So that means A minus C. Okay. So if n divides two integers and also divides their sum. So if A minus B is divisible by n and B minus C is divisible by n, their sum A minus C is also divisible by n. That's what it says. And if a relation satisfies all the three properties, that reflexive, symmetric, and transitive, it is called an equivalence relation. So in other words, congruence modulo n is an equivalence relation. Okay. It's always good to have an equivalence relation on a set. Okay. Later in group theory also we'll see. Okay. Here we are just talking about congruence, and we are seeing that it is reflexive, symmetric, and transitive. Okay. So in later group theory, you will actually see that it's always with using equivalence relation, will be deducing a lot of properties. Okay. And there is a notion of equivalence class. So what is equivalence class? Okay. In fact, in this case, see, for any equivalence relation, we call it equivalence class. But when we are talking about congruence modulo n, we can also call it congruence class. Congruence modulo n. Okay. Since our relation is this. So this is the general terminology, equivalence class. Okay. For an equivalence relation, something called equivalence class. What is equivalence class of A? Equivalence class is all the elements in the set which are related to that element. In this particular case, since we are talking about congruence, so it is all the integers x such that x minus a is divisible by n. We take this, then that will be an equivalence class or congruence class. Example, let's take n equal to 6 and let's take the element 2. What are the elements which are congruent to 2? Certainly 2 itself, because it's a reflexive relation. Okay. But minus 4 also, because 2 minus minus 4 is divisible by 6. Similarly, 8 is divisible. Minus 10. Okay. So in fact, you can see that, in other words, it is 2 plus 6k, because any element of the form 2 plus 6k, any integer of the form 2 plus 6k, you subtract 2, then it is divisible by 6. So in other words, these are all congruent to 2. But importantly, nothing else is congruent to 2. This covers all. Because if any other number is congruent to 2 mod 6, that means a minus 2 is divisible by 6. So a minus 2 is 6k. So a is 6k plus 2. In other words, these are precisely the elements in the equivalence class. So this is the equivalence class. Okay. And this is same as equivalence class also of 8. Okay, because this is, what is the equivalence class or congruence class of 2? The same as 8, because you can take any element here, you'll get the same congruence class. Why? Because of these properties. Okay, because if some x is related to, if x is congruent to 8 and 8 is congruent to 2, then x is congruent to 2. So if x is in the class of 8, x is also in the class of 2. And similarly, if y is in the class of 2, y is in the class of 8. So any element in the congruence class could be its representative. We can say it's a representative. It represents the class. This could be taken. So for example, this 6k plus 2, I can also take it as 6k plus 8, because I just have to decrease this k by k minus 1, then I'll get 8 plus 6 times some integer. Okay, so I could have replaced it by minus 4 also. So you can see that this equivalence class consists of elements which are congruent to 2 mod 6. So here we are talking about mod 6. That is our relation. An important thing to note is that congruence classes are disjoint. Okay. So let me explain why it is. That first thing to note is that okay, any element is in its congruence class because of reflexivity. Okay, because a minus a is always divisible by whatever n we are saying taking. So this is certainly true. But important property is two equivalence classes are either equal or disjoint. Okay, these are extreme cases. Okay, no overlap, no non-trivial intersection. You have two equivalence classes, then if there is one common element, then they will be same. Every element will be common. One common means all common. Okay, so either they're disjoint or they're equal. Okay, so how do I prove this? If they are disjoint, then it is fine. If not, there will be some common element. So suppose this congruence classes, the intersection is non-empty. That means there will be some integer x in both the congruence classes. Okay, so what does it imply? It means x is congruent to a mod n and x is also congruent to b mod n, and that will actually imply that a is congruent to b mod n, because it's like transitivity. First it is reflexivity. X is congruent to a, so by symmetric property a is congruent to x. A is congruent to b. Now let's take anything in the congruence class of A, and that means y is congruent to A. Okay, I forgot the mod n here, but anyway, it's clear that we are fixing the n. So if y is in the congruence class of A, then y is congruent to A, but A is congruent to B. So by transitivity here, this transitivity, so y is congruent to A and A is congruent to B, so y is congruent to B. That qualifies it to be in the equivalence class of B. And I can go in the reverse direction, because I started with this, I went in this forward direction. And in the backward direction, suppose take any element in the congruence class of B that it is congruent to B mod n, but B and A are congruent, which we saw already because of the common element x. Okay, x was this starting common element, but y is now any arbitrary element in this equivalence class B. So then y will also be congruent to A, and that will qualify it to be in the congruence class of A. So these congruence classes, if they have one common element x, then all elements are common. By the way, this is we are doing for the congruence class, but this is in general true for any equivalence class. So here this is not just true for the equivalence relation of congruence modulo n. It is true for any equivalence class, any equivalence relation. Okay. So equivalence classes are either equal or disjoint. Now, what is the advantage? Then we can view Z as a disjoint union of congruence classes modulo n. Because, okay, why am I saying? I'm saying that Z is a disjoint union of congruence classes. Okay. This, because if I take the union of congruence classes, that union is disjoint, because congruence classes cannot have any common element if we are taking distinct congruence classes. Why every integer is covered? Because every element, as I noted first, because of reflexivity, any integer will be in its congruence class. So this Z is a disjoint union of congruence classes modulo n. And by the way, this is just true in general also, that if I take any set S and I consider any equivalence relation, then the set is disjoint union of equivalence classes. and that is a big, that is a very useful thing. Okay, why? For example, in counting, suppose you want to count a set, but if you can put an equivalence relation, you just have to count number of elements in each equivalence class, because their sum will be the total number of elements, because there you don't have to worry about overlaps. Okay, because when you break down a set into disjoint union of subsets, then counting becomes easier, because you can just count the number of elements in each subset, and their sum, this sum will be the total number of elements. Okay, and of course, when we view Z, we are not interested in counting because Z is infinite. But when we have a finite set and an equivalence relation, then certainly we often count using equivalence classes. So an equivalence relation is a good thing to have on a set. Okay, so let me give an example. Let's take n equal to 6. Then certainly I can write Z as equivalence, disjoint union of equivalence classes. This is what I mean. Okay, any integer I take, let's say 100. Okay, 100 will bring, must belong to one of them. Where will it belong? So let's see, 100 leaves remainder 4 when I divide by 6. Okay, so which one of them leaves remainder? So 16, because yeah, so 100 minus 16 is divisible by 6. Okay, if I take 99, probably it's 9, because 6 into 15. If I take 98, similarly you'll be able to find 98 minus 8. Okay, so if I take 98, it is certainly 8. 97 will be also somewhere here. Okay, 97 should be in 13. Okay, yeah, 97 minus 13 is 84. Okay, and then 96 similarly. So any integer you take, it will be in one of them, and certainly they do not have any common elements. Okay, so that's what we are saying, that we can split a set into disjoint union of equivalence classes, and in this particular case, Z is our set and congruence mod n is the relation. So Z is disjoint union of congruence classes. Okay, now there's this notion of complete set of residues. Sometimes it is useful. So what is a residue? Because you take a representative of the congruence class, it is called a residue. Okay, I mean, for example, 8 is a residue of this class, but that could have been 2 also. There is no unique residue. I mean, this 8, I can also take 2 also. Okay, like that. Some representative you take, you call it residue. Then one thing to note is that how many distinct congruence classes are there? Take an integer n. How many distinct congruence classes are there? So we'll see that they are precisely n. And these can be taken as congruence class of 0, 1 up to n minus 1. Why is it so? It is because of division algorithm. Because by division algorithm, any integer a we can divide by n, and we'll have a remainder which will be lying between 0 and n minus 1. Okay, and you can see that this a and r are congruent. Why? Because a minus r is divisible by n. So any integer is congruent to its remainder modulo the divisor. Okay, any integer is congruent to the remainder modulo the divisor. So and the remainder is only one of them. Okay, remainder has to be one of them. So and yeah, so and why they are distinct? I said they are distinct. Why? Because if I take 2 of them, let's say any 2, let's say I and j, then certainly they will not be congruent modulo n, because I minus j, let's say I is bigger than j. Let's pick 2 elements I and j here. Suppose I is bigger than j, then what will happen? I minus j will be non-zero, and I minus j will be strictly less than n. because I is strictly less than n and you are subtracting j. Okay, so you'll be still less than n minus 1. On the other hand, I've taken I and j such that I is strictly bigger than j. So I minus j is not also 0. So I minus j is not divisible by n. So that's why we say distinct congruence classes. Okay, so there are exactly n distinct congruence classes modulo n. Okay. So what is a complete system of residues or set of residues? Then okay, so what is a complete? So a set of n integers a1 up to n is called a complete set of residues if any given integer x is congruent to exactly one of the ai's. Okay, exactly is important. Exactly is important because it should not be like that it is congruent to two of them. Okay, just you cannot just pick any n integers. They have to be distinct mod n. They have to belong to different congruence classes. Okay, but there need to be n of them because we know that there will be n distinct congruence classes. So exactly that is the meaning. Let's look at some example. For example, this 0, 1 up to n minus 1, it's a complete set of residues. Because anything I take, then any number a has to belong to congruence class of one of them. And exactly one of them. Because when I divide any integer a by n, the remainder will be exactly one of them. It cannot be the remainder will be 2. I mean, remainder is unique. Okay. So that means exactly one of them will be congruent. For example, minus 2, 7 and 12, it's a complete set of residues. Okay, I could have taken 0, 1, 2, but that's a non-trivial, I mean, there was a very trivial example. Okay, so hopefully I've got it right. Well, maybe there's already a mistake here. Okay, let's see, because this is the one where it is 0 mod 3. This is 1 mod 3, but unfortunately this is also 1 mod 3. This minus sign has to go. I'll correct it. Okay, what's the problem? Because 7 and minus 2, they are congruent modulo 3. So certainly this is the wrong example. This minus sign should be deleted. Okay. Otherwise, what happens? Then what happens? 1 is congruent. Okay, so let's take a bigger number. Let's take say 13. 13 is congruent to both of them. 13 minus 7 is divisible by 3, and 13 minus 2, which is 15, is also divisible by 3. So this example, I have to omit minus 2. I mean the minus sign. Okay, so this is not a complete set of residues modulo 4. Okay, what we are taking minus 2, 7, 12, 9, 14. Of course, simple example would have been 0, 1, 2, 3. That would be complete set of residues. And why this set is not there? Because there is a redundancy. Okay, two of them will be congruent, like minus 2 and 14. Okay, like 12, minus 2 and 14. Yeah, because 14 is congruent to minus 2 mod 4. So for example, if I take 22, 22 is congruent to 14 mod 4 and 22 is congruent to minus 2 mod 4. So 22 is being congruent to two of them. That is one way to see it. Another way to see is that there is a redundancy, that this itself is congruent to this. Okay, so if we leave this out, then I'll get a complete set of residues. For example, this one should be a complete set of residues because this will represent like remainder 0, remainder 1, remainder 3, remainder 2. Okay, this is a complete set of residues. Okay. So because another obvious set would have been this minus 2 is like 2, 7 is like 3, 12 is like 0, and 9 is like 1. Okay, if I take the remainders. Okay, so this is quite obvious that anyway we are giving it the status of a theorem. Two arbitrary integers a and b will be congruent if and only if they leave the same non-negative remainder when divided by n. Okay. So in other words, two integers are congruent modulo n if and only if they leave the same remainder when divided by n. Where did I say non-negative remainder? Because yeah, there are certain cases where we also consider like negative remainders, but of course by default it is the non-negative remainders. If we don't specify, it's basically non-negative remainder. Okay. Because when we divide 3 by 4, I can say 3 is the remainder, but sometimes I can say -1 is also the remainder. Okay. So sometimes that is also useful. For example, when we discussed Euclid's algorithm, we said that in fact it is best to take the remainder in absolute value smaller than the previous divisor. Okay, like that. Okay, so let's see how we prove this. Suppose A and B leave the same remainder. Then certainly, if I subtract them, then A minus B will be a multiple of n. Okay. So if they leave the same remainder, they are congruent, no doubt. Okay, and suppose they are congruent. And let's say A is B plus Kn, because that's what it means. That if A is congruent mod n to B, then this is it. Now suppose, well, okay, so there is again a typo. Let's say, okay, so I'll have to cut this part. Okay, forget this part. Suppose B has remainder R, then what will it imply? Then A will be B plus Kn, which is NQ plus R plus Kn. Okay. Because A is B plus Kn, and what is B? B is NQ plus R. Forget this is not, I mean, I'll have to delete this. Okay. And then what we get is N times something plus R. Okay. But yeah, this is a quite trivial enough explanation that you can figure out yourself. Okay. So just that V is congruent to B mod N. Then if B leaves remainder R, A leaves remainder R as well. So this I have to cut. Anyway, I'll correct it when I upload the slides. Okay, so properties of congruence. What are the further properties? Already we saw that congruence mod n is an equivalence relation. Okay, that is reflexive, symmetric, and transitive. Okay. Now let's see what else can we say. Okay, that if it behaves Am I audible now?
Yes, sir.
Okay. Okay, so let me see what was doing. Okay, can you see the slides now? Can you see the
Yes,
slides?
sir. Yes, yes, sir.
Okay, so I suppose I covered up to this. Now we are saying properties of congruence. Okay, so we already saw that congruence modulo n is an equivalence relation. Okay, in addition to that, it behaves nicely with respect to addition and multiplication. Okay, what do I mean by that? That if I start with two congruent numbers, I mean two pairs, A is congruent to B and C is congruent to D, then I can add A plus C, which will be congruent to B plus D. And if I take AC, if I take the product, then it will be congruent to the product of B and D. So it behaves well with respect to addition and multiplication. And suppose I have just one pair and I will take any random C, any integer C, then certainly A plus C will be congruent to B plus C and AC will be BC. Okay. And thirdly, if A is congruent to B mod n, then A to the power k will be B to the power k mod n for any positive integer k. Okay. And clearly, for example, once we prove the first one, the third one is trivial because I can say A is congruent to B and again I can take A congruent to B. So if then I multiply, I'll get A square congruent to B square. Then I take A square B square and AB. Then I get A cube congruent to B cube. So certainly this follows from this, and this one also follows from this only because I can say C congruent to C here because I know that C is always congruent to C, and then this also basically nothing but a special case of this. So only thing to prove is this first property. So the first property also can be trivially observed. For example, let's prove the multiplication. Since A and B are congruent, let's say A is B plus Kn and C is D plus Ln. Okay, because A and B are congruent and C and D are congruent. Then let's see what is AC. I just multiply it out and I find that BD plus some multiple of n. So that means AC is congruent to BD mod n. Okay. It is obvious, but we are doing it because for a purpose. Okay. So okay, this is just a comment that we can, the other two properties follow from this. Okay. So that actually tells us that we can define addition and multiplication on congruence classes. That is important. Okay. That means suppose I have two congruence classes A and B. So I can define their sum to be A plus B. Okay, it's not equal, it should be A plus. Okay. And their product is their product and then congruence class. In other words, addition commutes with taking congruence class. Okay, take congruence class and add, or add first as integers and then take congruence class. It's the same thing. Or you multiply the congruence classes, okay, or whether you multiply as elements and take their congruence class. It's the same thing. Why is it so? Because we proved it actually. Okay. So what would have been the problem? Because what would be the problem in general when we define this operation we are trying to define on equivalence classes? We are not now defining on integers. This is the addition on integers, which actually unfortunately is appearing as equality, but actually it's a plus. Okay, let's focus on this one. Okay, here see this multiplication we know and this congruence class we know. But here we don't know how to multiply congruence classes. What could have been the potential problem? Suppose I take residue A, but you take residue A dash. You take a different representative. Or I take B, but you take B dash. So my product will be AB, but your product will be A dash B dash. But we need, as equivalence class, they need to be same. So A dash B dash should be congruent to AB. but that is precisely ensured because we showed that if A is congruent to A dash and B is congruent to B dash, then AB is congruent to A dash B dash. So that means whether I take the product as AB and then take congruence class, or I take A dash B dash and congruence class, does not matter. Okay. Similarly for plus. Okay. So as I said, suppose I have the same equivalence class but with different representative. For example, mod 6, this could have been, my choice could have been 2, your choice could have been 6, so 8. Okay. Or my choice could have been 3, your choice could have been 9, modulo 6, they are same. Okay. And so I would be, so for example, if I add, I will be getting A plus B, but you'll be getting A dash plus B dash, but not a problem because A is congruent to A dash mod and B is congruent to B dash mod. So if I sum them up, they'll still be congruent. And in fact, their product will also be congruent. And that will mean they are sum as equivalence class, their equivalence classes are same. Because if two elements are congruent, their equivalence classes are same. Anything congruent to the left hand side will also be congruent to right hand side and vice versa. So this is same. So there is no problem. Okay, this AB equal to A dash B dash, it's appearing outside the slide. Okay, anyway, let's illustrate this with an example. Let's take n equal to 12. Okay, let's see how I add equivalence class of 9 and equivalence class of 7. And I want to emphasize that there is no ambiguity even if I choose 9 and 7 differently. For example, in place of 9, I could have chosen 21 because 21 minus 12 is 9. So they are in the same congruence class. Similarly, 7 and 19 are also in the same congruence class because their difference is divisible by 12. So if I add them as 9 and 7, I get this addition as 16. And if I add as 21 and 19, I get 40. But that's not a problem because we'll find that 40 minus 16 is divisible by 12. 16 minus 40 is divisible by 12. So as sum, they are same. As equivalence class, they are same. As congruence class, they are same. Similarly for product, I can multiply 9 and 7 as 63. And you can multiply with your choice, 21 and 19, and you get 399. Still not a problem because 63 will be congruent to 399. So their equivalence classes will be same. So we can transfer the notion of addition and multiplication from integers to congruence classes modulo n for any n. Okay, it's like you can say it is inducing. Okay, the addition on the set of integers induce an addition on congruence classes modulo 12 here, but in general for modulo any modulo. Similarly, multiplication. Okay. Okay, so another important property of congruence is that how do I cancel? Just like, okay, in general, we can cancel like if AX equal to AY, forget congruence. If we have integer multiplication, if AX is AY and A is non-zero, I can cancel A. I can say that AX equal to AY implies X equal to Y. Okay. Similarly, if I want to do such cancellation, I have to be a bit more careful because I have to keep track of this GCD of these two, which is quite obvious if you think about it, that if AB equal to AC, it's not that I just cancel A, I may have to cancel something from N also, which is the GCD of A and N. Okay, let's take G to be the GCD of A and N. Then if I'm cancelling A, then it is not congruence mod N I'm getting, but N mod T. Okay, why is it so? So was it saying that AB minus AC is a multiple of N? So let's say AB minus A times B minus C is AB minus AC is Kn. Okay. Now GCD of, okay, so this should have been D. Okay, this is not 1, this is D. Since GCD, let's say GCD is D, okay, this number is D. Okay, if GCD is D, that means, okay, so maybe it will be best if I rewrite this. What I intended to say is GCD of A and N is D. So A I can write as, okay, so I'll write this. I'll rewrite this because otherwise it might be confusing. Okay. So anyway, so I'll rewrite these slides. Okay. Maybe, okay, so these 3 slides maybe because there's a typo and also, yeah, so I'll rewrite this and then upload. Okay, so I'll maybe discuss it. This will be the starting point tomorrow. Okay, I'll start from here. Cancelling, how they cancel the GCD. Okay. Yeah, so okay, so if you have any question, let me know. And probably okay, so this recording I also did.